Welcome to a presentation on quadric surfaces. Today we will be dealing with some of the examples of these quadric surfaces, and we'll also be learning how to sketch the graph of them. So what are quadric surfaces? Quadric surfaces are defined by the second degree equations of x, y, and z, or actually just three variables. It doesn't have to be x, y, and z, it just has to be three variables. So x squared, y squared, and z squared, the equations that include them. So historically, the quadric surfaces develop almost analogously with the conic sections. You guys remember what conic sections are, right? They include the parabola, the ellipse, and also the hyperbola. So it developed during the time of the Greeks, which were a remarkable feat, but they really didn't move as close as to what we know now. The theory of quadric surfaces aren't as close as to what we know now because they didn't have the tools that were invented by Descartes. They didn't have the tools of the coordinate systems that we are so familiar today. And it's only after the 17th century that the theory of quadric surfaces, and conic sections start to move forward and gain momentum. So today we'll be studying a few examples of these quadric surfaces, and they are the ellipsoid, the elliptical paraboloid, the elliptical cone, the hyperboloid of one sheet, the hyperboloid of two sheets, and also the hyperbolic paraboloid.
Now we have a short review on conic sections. The general form is ax squared plus by squared plus cx plus dy plus e equal to 0. Actually, in this section, we are not interested with the cx and the dy. We only deal with the ax squared plus the by squared. Because the cx and dy, they are only responsible for the shifting of the graphs. So here are the examples of the conic sections. We have parabolas, we have ellipses, and the hyperbolas. First of all, we look at the parabolas. The standard form for parabolas is y equal to a times x minus h squared plus k.
Notice that the ordered pair h, k is the vertex of the parabola.
Let's look at the graph. So this is how a parabola looks. If the h is positive value, you see the graph is shifting rightwards. Okay, if h is a negative value, then the graph will shift leftwards. Okay, so the same thing goes to k. If the k is positive, the graph will slowly shifting upwards. So this is how the parabola looks.
Right, that's the parabola. Next we'll talk about the ellipse. The ellipse is expressed in the standard form by x squared over a squared plus y squared over b squared equals to 1. Now here's the graph of an ellipse. So this is the graph of an ellipse. Now notice that the longest distance between 2 points of the ellipse, which is parallel to the x-axis, crosses the center of the ellipse. So in other words, this line over here, this distance, is longer than all the other distances that are parallel to the x-axis. A similar case can be said for the horizontal distance, that the horizontal distance, the longest one, crosses the center of the ellipse. So for convenience sake, let's call this longest distance that is parallel to the x-axis and crosses the center of the ellipse, the length, and the horizontal distance, the height. Now recall that the major axis is the longest between these two, length and height, and the minor axis is the shorter one. So in this example, the major axis is this length over here, the x-axis, the length over the x-axis, and the minor axis is this height over here. Now the major axis and the minor axis is determined by the a value and the b value. Notice that the a value is bigger than the b, which is displayed here via the slider. So if we slide the b value so that it's bigger than a, we notice that the major axis changed. Now the major axis is this height over here, and that the minor axis is this length here. Now a caveat. What if a equals to b? What if a equals to b? What we get is a circle. And in fact, a circle is a special case of an ellipse when a equals to b. Right, so that's a summary of the ellipse. Let's move on to the hyperbola. The hyperbola is expressed in the standard form by this equation: x squared over a squared minus y squared over b squared equals to 1. Let's look at the graph. So this is a graph of the hyperbola. Notice that that the graph doesn't intersect the y-axis here. This is because the expression here has a negative sign. Think about it. If x is equal to 0, which is at this point, right? You could simplify, you can bring this negative b squared over to 1. So it'll be y squared equals to negative b squared. But this is impossible because y squared is always a positive number. So therefore it's undefined over here. It's an imaginary number, a complex number. So intuitively, you could think of it like this: that whenever a variable has a negative sign in front of it, you could always regard that that's the axis where the graph doesn't intersect. So here's an example where the x value, the x variable, has a negative sign in front of it. So you could see that the graph doesn't intersect the x-axis.
Okay, so that's all for the conic sections. Now we move on with the quadric surfaces. Firstly, we have cylinder. Normally we think of cylinder as a circle with extended length, but actually cylinder can be any curve with extended length, and we can consider the circle as one of the curves. Next, remember we have another 6 more quadric surfaces, which are the ellipsoid, elliptical paraboloid, elliptical cone, hyperboloid of 1 sheet, hyperboloid of 2 sheets, and the hyperbolic paraboloid. They all can be expressed in the special equation given below here. The ax squared plus by squared plus cz squared plus dz equal to e. To draw quadric surfaces, we need to examine 4 things. We have to know the xy trace, we have to know the yz trace, the xz trace, and the intercepts of x, y, and z. To find out the xy trace, we can equate z to 0. To find out the yz trace, we can equate x to 0. To find out the xz trace, we equate the y to 0. To find out the x-intercept, we equate the other two variables to 0. The same things goes to y and z intercepts. First of all, let's look at the ellipsoid. Ellipsoid has the standard form of x squared over a squared plus y squared over b squared plus z squared over c squared equal to 1. In case that in exam you can't remember this equation, you can try to draw the quadric surfaces as mentioned in the previous slide. So first of all, we find out the three traces. The first one is the xy trace, the second one is the yz trace, and the last one is the xz trace.
Remember, to find the traces, simply equate the other variable to 0.
Notice that the three traces here are all ellipses. So let's look at the graph of an ellipsoid. So this is how an ellipsoid looks like. Let's look at the xy trace, which is here. So we see an ellipse, and then let's look at the yz trace. And so we see an ellipse as well. And lastly, the xz trace. And obviously, this is also an ellipse. So that's all for the traces. Now let's look at the intercepts. So if you want to find the x-intercept, we just equate the y and z to 0. So we find that x squared equal to a squared. For the y-intercept, we find the y squared equal to b squared. And for the z-intercept, we find the z squared equal to c squared. So if we draw an ellipsoid, the x-intercepts will be plus and minus a, and the y-intercept will be plus and minus b, and the z-intercept will be plus and minus c.
Next, we will look at the elliptical paraboloid. The standard form is thus: x squared over a squared plus y squared over b squared equals to z over c. So to sketch the elliptical paraboloid, what you need to do is to find the traces. Now you can think of the traces as this. You can think of it as a perspective such that your viewpoint is perpendicular to one of the graph's axes. So in other words, you treat one of the variable as a constant, so that what you're viewing is actually two-dimensional. So to find the xy trace, or the yz trace, or the xz trace, we by default would assume that the other constant is 0. But sometimes that's not the case. For example, for this graph, if we equate z to 0 for the xy trace, we find that x is equal to 0 and y is equal to 0. This would give us just a point, which wouldn't help much, as it's not going to tell us what it's going to look like at the width. So to find out, we have to substitute the z value to some other constant. So we could equate z, let's say, to 1. If we do that, we find that this equation resembles the equation of the ellipse. So what's happening here, you could imagine, is that at z equals to 0, there is no ellipse, it's just a point. But then for each increasing z value, the x, y trace is an ellipse. For the yz trace, simply equate the x value to 0. What you find is an equation that resembles a parabola. This is similar to the xz trace. So this is the graph of an elliptical paraboloid. So you can see that the xy trace gives you an ellipse. But when z is equal to 0, it starts at a point. And as for every increasing z value, the ellipse increases its size. For the yz trace, we see that this forms a parabola. For the xz trace, we find that this graph forms another parabola. To find the intercepts of the elliptical paraboloid, we simply equate the other two variables to 0. So for the x-intercept, we equate the y variable and the z variable to 0. For the y-intercept, we equate the x variable and the z variable to 0. For the z-intercept, we equate the x variable and the y variable to 0. What we find is that x equal to 0, y equals to 0, and z equal to 0. Let's now look at the elliptical cone. The standard form of an elliptical cone is given by the equation x squared over a squared plus y squared over b squared is equal to z squared over c squared. To sketch the graph of an elliptical cone, we must find the traces once again. To find the xy trace, simply equating the z value to 0 is insufficient. This is because if you do so, the solution for x and y must only be 0. This would result in just a point, which is not enough information for us to draw the width of the graph. So we must assume z as some other constant c, such as 1. Then the equation will result an equation that resembles an ellipse, such as this. To find the yz trace, simply equate the x variable to 0. This would result in an equation such as this. Now, as you can recall, this equation resembles the equation of a line. But notice that there's a plus or minus sign here, meaning that there's two lines that resembles a reflection of the other. For the xz trace, a similar case is found. So this is the graph of an elliptical cone. Now as you can see, the xy trace gives you an ellipse. But when z is equal to 0, this results only in a point. For the yz trace, we see that the graph gives us two intersecting lines. For the xz trace, we see a similar case. Now to find the intercepts of the elliptical cone, we simply assume the other two variables as 0. Doing so gives us x equal to 0, y equals to 0, and z equals to 0.
So that's all for the elliptical cone. Now we move on with the hyperboloid of one sheet. So we have the standard form of x squared over a squared plus y squared over b squared minus z squared over c squared equal to 1. If you need to draw the graph of hyperboloid of one sheet, once again you need to examine the traces. First, we have the xy trace where we just equate the z equal to 0. Then we find that the xy trace resembles the ellipse. Next, we equate the x to 0. We find that the yz trace resembles the hyperbola. The same goes to xz trace where we equate the y equal to 0. We have the hyperbola again. So this is generally how a hyperboloid of one sheet looks. Let's look at the xy trace. Without the confinement, actually the xy trace is an ellipse. Okay? For the yz trace, it's over here. We have hyperbola. Here is the hyperbola. Okay? And for the xz trace, we have once again the hyperbola. So that's all for the traces. Next, we look at the intercepts. So for x-intercepts, we just equate y and z to 0, and we find that x squared equal to a squared. And for y-intercept, we just equate x and z to 0. We find that y squared equal to b squared. But for z-intercept, here comes a problem. If we equate x and y to 0, we will find that z is a complex number. So we look at the graph again. We see that for z equal to 0, we can't have a definite value. There's a hole in this graph, okay, along the z-axis. So there's no defined value for z-intercept. Next, we look at the hyperboloid of two sheets. The standard form of this is z squared over c squared minus x squared over a squared minus y squared over b squared equal to 1. So to draw this graph, we once again have to find out the traces. To draw this graph, first of all, we need to examine the traces. For xy trace, in this case, we can't equate z equal to 0 because negative x squared over a squared minus y squared over b squared can never be 1. So let's replace 0 with square root 2c. Then we get the whole thing become x squared over a squared plus y squared over b squared after some operations. Okay, so for the yz trace, we just equate the x to 0, then we find that this is the hyperbola. And for the xz trace, we just equate the y to 0, and we once again find a hyperbola. So this is how hyperboloid of two sheets look. Let's look at the xy trace. So this is an ellipse. And let's look at the z equal to 0, we find that there's nothing here. But as z equal to square root 2c, here we start to have ellipse, and the ellipse slowly becomes larger and larger as the z values grows larger and larger positively and grows smaller and smaller negatively. Next, let's look at the yz trace. So this is the yz trace. This is the xz trace, sorry. And we find that this is a hyperbola. Next, let's look at the yz trace. Once again, we see a hyperbola. Okay? So that's all for traces. Now we look at the intercepts. Notice in this case, the x-intercept does not exist because in here we find that the x is a complex number, and the same thing goes to y-intercept. Okay, so let's look at the graph again. Along this axis, this x-axis, we find that there's no interception. Okay, and for this y-axis, there's no interception too. And for the z-intercept, we find that z squared equal to c squared. It means z equal to plus minus c. Look at this graph again. Along this axis, we find there's two intercepts, which is the positive c and the negative c. So that's all for hyperboloid of two sheets.
Lastly, let's look at the hyperbolic paraboloid. The standard form of the hyperbolic paraboloid is given by the equation y squared over b squared minus x squared over a squared equals to z over c. To sketch the graph of the hyperbolic paraboloid, we need to find the traces once again. In this case, we have to find two xy traces. This is because when we solve y squared over b squared minus x squared over a squared equals to z equals to 0, we get the equation of a line given here. But if we let z equals to some other constant k, we get the equation of a hyperbola. To find the yz trace, simply equate the x variable to 0. Doing this will result in a parabola equation. For the xz trace, a similar case is found. So this is the graph of the hyperbolic paraboloid. As you can see in the xy trace, you can see two hyperbolas here. This is because z can take over any value. So if z is equals to a positive number, then this would be the hyperbola. But if z takes on a negative value, this area here would be the hyperbola. Also notice that if z is equal to 0, which is at the middle point here, the two lines are defined. Now let's take a look at the yz trace. The yz trace gives us a parabola. Similarly, the xz trace gives us another parabola. This time it's concave downwards. To find the intercepts of the hyperbolic paraboloid, simply assume the two other variables as 0. Doing so, you will get x equals 0, y equals 0, and z equals 0. That's all we got for quadric symphysis. We hope you've enjoyed our presentation. See you soon.